So welcome again, everyone. For today's session, we'll implement for each loops in the shape and form that you see in this code snippet, and we will lower them into roughly the C# equivalent. We will call the get enumerator on the enumerated sequence, and then in the while loop we'll call move next, and we will extract the current property of the enumerator into the variable that the user specified in the loop as the iterator variable. It will have two syntaxes, one with explicit type parameter and or explicitly typed iterator variable, I guess, and one with an implicitly typed iterator, as it's quite usual for us to infer almost everything that's function local, so it makes sense to have it as well. Now, when I say that we lower it to an almost C# equivalent, if you know the C# way of iteration well, you know that we should wrap this into a try finally block and call enumerator.dispose in case it's a disposable enumerator, but we don't have either try-catch blocks, neither try-catch blocks nor are we able to do a type-checked cast at runtime currently, so this will have to do for now. What do we have to do to support this in the compiler? First, we'll have to do syntax analysis. That will consist of implementing Lexing. We'll have two new tokens. One will be the for keyword, and the other one will be the in keyword here. Then we'll have to implement parsing. We will add a new syntax node to support this construct, and we will parse into this construct in the parser, naturally. After that, we'll move on to semantic analysis. We'll have to do two things. First, we'll implement binding, then flow analysis. Now, there is a bit of Roslyn terminology here. I'll try to explain as we go, in case anyone is not familiar with the Roslyn compiler. I'm not that familiar with it either. I know bare bones, and Roslyn was the compiler that we try to base ours on, so the structure might be similar here and there. And finally, we will lower the for loop into this while loop construct, so we don't have to implement code generation ourselves at all. Let's start this session by actually verifying that we are able to lower into this construct. Let's write a very simple enumerator. Now, so we will essentially write a loop with this construct and try to print the numbers from 1 to 10 using this. So what I'll do is what I usually do when I start implementing a feature is that I'll install the SDK somewhere. We have a few helper scripts in the compiler repository under scripts. You can see them here. Some of these are NuGet packages that I just have locally here because some scripts compile here. But for example, installing the toolchain means installing the entire compiler, SDK, and everything under a folder. Now I have a folder in my C called streaming, so we'll install it there. And just to have a bit of a structure, we'll call this for each loops. And hopefully the script creates the new project and the SDK there locally. Okay, we can test if that actually happened. Now this should have generated a simple hello world. Okay, it seems to work. So let's open this project. Now, fortunately, our Our extension is smart enough that it can recognize that this is a Draco project, and it can generate the CRUD that is needed for VS Code to automatically execute here. So now I can just press F5 and we should be running here, no problem. All right, wonderful. So let's try to write a manual iteration. For that, I'll import enumerable from link. Now, you might ask, why don't we use arrays or lists? Now, there's a very good reason. We do not yet support nested types from metadata. We don't import them yet. And unfortunately, the list enumerator is a nested struct, I think, which we definitely don't support, but we can check it out. I don't know if that changed. Yep, it's an unknown, which means that it could not resolve this type reference. So we will use something like enumerable.range, which fortunately uses the interface, which we do support loading. So we can construct a range. Let's go from 0 to 9 inclusive. I think that should be it. Let's actually try to run it and see if we get the numbers from 0 to 9. It doesn't navigate us to the output window. What happened here? Let's try to run it from here. Maybe we're stuck in an infinite loop or something. Nope. Okay, I don't know what's wrong with... Oh, sorry, it's the debug console that we should have looked at. Okay, so it seems to work fine. That means we can start actually implementing it now. Let's write a snippet that we want to be able to compile by the end of this session. So let's use for. And let's just write this same loop that we had previously, but in this more terse form. Now we will see that the language server is quite unhappy about this syntax. Obviously, it won't be able to recognize quite a few things here, but we will have that when we implement Lexing and parsing it. So let's jump into the compiler and let's hack away at Lexing first. Now, the first thing that we'll need to do is add 2 new token types for the 2 new keywords. I think we have keywords grouped here, and we have them in alphabetical order, so I'll try to add them in alphabetical order as well. So we have F here. I think that 4 will come here. And in will come just a bit after. So we have internal. Now the shorter keyword will come first. That will be just an arbitrary ordering rule for us, I suppose. And with this, we have essentially added the keywords as token kinds. We still don't lex them yet. So let's do that. We jump into the Lexer, and fortunately in the Lexer we don't have a lot of things to do. We have the keywords grouped here, also in alphabetical order. So let's just add them here. And also in. So this should be enough for the Lexer to recognize these two new tokens. But lexically we have to do a bit more. We have a bunch of utilities that work on tokens, and one thing that we have to do with tokens that have a single texture representation is to write the logic that turns back token kinds into their texture representation, which we mostly use for error reporting. So this will be in the syntax facts maybe. I don't actually remember. It could be in the API as well. I don't know what we expose. Yes, it's in the API. So first off, we'll need to be able to turn back the for keyword into its text representation, and we will have to do the same with in. Now, this might seem a bit redundant. We should be able to have this knowledge in one place. We haven't factored this out yet. I just don't see a very nice way without writing another source generator using reflection and attributes, neither of which I'm too big of a fan of. So with this, Lexing should be done. If you check the current errors, we get things like undefined reference to for. Now let's try to recompile the language server and see what happens. Well, maybe an even simpler thing, because I would have to close the VS Code session I have here to be able to reinstall the Lang server. One thing we could do is use the CLI frontend and redirect that to this folder that we are working in. So it's in streaming and foreach loops. Oops. So if you run that, we'll likely get a bunch of undefined references to things in the BCL. We will solve that in a second, but there are no undefined refs to for anymore, which means that it's finally its own token, which is nice. So let's solve these undefined references. Now the reason we have undefined references when we run the CLI is because MS-build passes us all the metadata references that we need when we compile for a certain .NET version. So when we target .NET 7, we will get all the .NET 7 BCL metadata refs that we need. Now, obviously, if I run it from here, I have nothing specified. So what I usually do when I start a local test session is that I steal the way our test project runs with BCL references, which is to use this basic reference.assemblies package, which just contains all metadata refs for major .NET versions. So we'll slap on this reference, and then we will have to pass this in for the compilation. Now we have in the tests, we pass them on here. We will trim this down a little, but this is roughly what we will need. And the CLI is pretty simple. We have a run and a compile that we would modify. Here you can see that the metadata refs are passed in as file info. Now instead we will just use this library to tell us what we need. And we really don't need that concatenation logic here. And we'll also modify run in case we want to immediately run the code later. Now from the CLI, we should just get some pause errors, but okay, the things about the undefined references to system and such have disappeared. Now obviously we have things like undefined reference to I, and we're not surprised by that. The parser got pretty confused about what this could be. Now since we are essentially done with Lexing, let's commit this. This is a good point to save our progress, even though we didn't do much. Now, I don't know what this change is. I might have dragged something, so I'm just going to discard this right away. And these two, the CLI modifications, we won't commit. So we just commit the Lexer modifications onto a new branch. So we're done with Lexing. We won't publish this branch yet. The next thing on our list, if we take a look, should be parsing, which means adding a new syntax node and then modifying our parser logic, of course. Now, adding a syntax node is not as simple as writing a class. It's actually way simpler. If you know a bit of Roslyn, we use something called red-green trees. So we have essentially two syntax trees. This idea originated in Roslyn. They wanted an immutable tree that we can also navigate both ways. So we can go recurse down on the children, but we can also go up the parent. So the way we do that, and the way Roslyn does that, is that we have an internal tree representation that's called the green tree, and then there's a wrapper tree called the red tree. And because of this duplication and all the caching that has to go behind the scenes, this is all generated from an XML file, and we have a source generator set up that always regenerates the tree when the XML changes. So we will open up the compiler in VS Code, and we should have a, let me close all these windows. We should have a file called syntax.xml, and here you can see all the syntax nodes. Now, because there are Draco files in the repository, the Draco extension will get pretty confused. This is something we'll have to debug eventually. Now we'll just cope with it. So what I'm going to do is I'll search for while expressions. If you didn't know, the language essentially calls almost everything an expression. They might just return a nullary value. In our case, we call that nullary value unit. And the same will be with for each loops. They'll be called for expressions. And we will just hammer the while node here into the for loop syntax node. So we don't have a while keyword, we have a for keyword. And we also have a safety guard here that always checks what kind of token is being passed in here. So we will have to make sure to change this as well. So after the for keyword, we obviously have an open parentheses. And well, this is in the condition, but before the, I don't know what this is called in Roslyn. Let me show what portion we're at here. So if you look at the example, after the for keyword, we have an open parentheses. I do not know what Roslyn or C# calls this. Let's actually paste this here as a comment, as a guide. So we will just call it the loop specifier, or the iterator, I guess. Someone will correct me about what this is called in C# anyway. Then we can rewrite the documentation for this. After that, we need an iterator variable, which is going to be a, let's call it iterator. And this will have to be a syntax token as well. After that, we don't have a close parentheses yet. We will have an in keyword. I'll just copy the for keyword field here. It's easier. Okay, so we are here. After that, we will have an arbitrary expression for the sequence that we're iterating. This isn't a token. Now I just noticed that I'm missing the safety check for the iterator name. This obviously has to be an identifier. Any other token passed in will result in the the syntax node constructor to throw an error saying that this is an invalid token. So this is why we did that. So after that, we're here. We expect a close parentheses. So I called it iterator here, so I'll call it iterator here as well. And finally, we will have the portion that we evaluate repeatedly. And we substitute each element into the iterator variable while we evaluate this block. Well, this is just a very rough description of what a for each loop does. It's probably not needed for people who work on compilers, but we started this style of documentation. Maybe eventually we'll find some better use for it. Now we're just sticking with it. So this should be it in terms of the syntax node that we need to create. Except one thing, in the beginning I mentioned that there's another syntax that allows the type specifier for the iterator variable. So let's add that as well. It should be an optional element. And I think we have a type specifier syntax for that, which is essentially just a grouped, just a node that groups the colon and the type together into one, so we can make both be contained in a single field and make it nullable. Now this is because a few places use a type specifier, like variables or the return type of a function. So that's why this is a separate node. Now this can come after the iterator variable. So let's add this field. The name will be iterator type. Yeah, and we need to make it optional, of course, otherwise it would be a required element. Okay, let's try to write the parser logic for this, which is hopefully pretty simple as well. The parser is a bit more scary than the Lexer, but we should manage. Now let's open up the parser, and the first thing that I'll do is check how the while loop is being parsed. It's here, and we're going to copy paste that. Obviously the internals will have to change a little bit. So instead of a while keyword, again I'm going to write the loop syntax here, so it's easier to track where we're at. So first we consume the for keyword, then we need an open parenthesis, just like in while. After that, we will need the iterator variable. After that, we have an optional type specifier. We can check if we need to parse a type specifier by checking if the next token is a colon. actually forgot what I called the type specifier in the node. Iterated type. Yeah, it might be better to call it element type. Peak, I think, should return the token kind. Yes. Okay, we have parsed the optional type specifier. Then we expect the in keyword. Then we need to parse, well, not the condition, but the sequence. We need the close parentheses, that's correct. And finally, we need to parse the body. So most of the while expression parsing code was useful. Now we just need to modify the constructor. As you can see, the constructor for this new syntax node is already generated along with the class. The source generator runs as soon as the XML has changed or something, or VS runs it in the background. I'm not entirely sure, but it's pretty responsive. And that should be it. Now, obviously, we don't call this yet, and the simplest thing to do is check where this is called. It's being called here, so we will add the for as well. Once we have written this parser logic, and then we just essentially always look at similar constructs that have been written before, because the parser logic is not that trivial. We had some different problems to solve than the C# parser. The C# parser is obviously more complicated than this one, but we have expressions and blocks that can return types, and the last statement can be a curly brace statement that might be a value, so we have to carry around this context thing here and there. So usually when we add a new construct, we just find a similar structure and copy that. Now we need to call the for expression, and for safety we're going to find all the references to the while keyword and check where we are doing extra checks, or where we call this control flow parse control flow expression from. Obviously this assertion needs to be updated. And let's check the references for the keyword while within the parser. Okay, we have a list of expression starter tokens. These are the tokens that, well, can start an expression. Since for is an expression as well, we add it to the set. This is statement parsing, and where the while is allowed, we allow for as well, so that can be added. This is the assertion where we added the for just previously. This is parsing a control flow expression. Yeah, this is the same method, we added it. This is the block parser. This is one of the more convoluted parts, because this is where we need to parse optional semicolons and such. Now the while expression is just as permitted here as a for, so we add that. This is the while parser, we don't need to do anything here. This is the for expression, and thank heavens this told me that I have a while keyword here instead of a for. We replace that. This is an atomic expression. Yes, the highest precedence things in during precedence parsing are atoms, which are grouping numbers, identifiers, other literals, and obviously the keyword constructs like while, if, for, or even a block. I think we should be parsing a block here. Yep, and that's why the curly open is here. Okay, let's check what this is. This is the formatter. We don't care about that anymore. Okay, that means we're done with the parser. Now let's try to run it. Okay, we have crashed during binding, which is wonderful because that means that syntactically this has parsed. There are no parse errors here. Now let's check the explicitly typed version. Let's see if this parses as well. I think so. Let's look at the output. No diagnostics here. Okay. So this means that the for loop node has been parsed. Let's actually check the syntax node, what it contains. So as you can see, it pretty prints the source code that it was parsed from, but that's not the interesting part. We can see the for keyword indeed containing the for, the element type containing the type specifier, the iterator is indeed this I identifier that we specified, and we have a bunch of other crud here. Now, if we don't specify the element type, we should get a null in that field. Let's just check that as well. Yep, it's null. So it looks like this part successfully. So we can move on to binding. Let's commit this because we have just written the parser logic for this. I won't be too sophisticated with my commit messages. This is because we mostly squash PRs, so it's mostly lost, and these commit messages won't be that valuable later anyway. Okay, I think this is a pretty nice point for a break before my voice starts cracking and I have a sore throat. So let's take 5 guys and we'll continue at 3:10 if you look at my system clock here. So all right, be right back, guys. Okay, let's continue. So we are done with the syntax part, and now we will delve into semantic analysis, which is undoubtedly the more complicated part of the compiler, and usually when we add a feature, semantics is almost always more complex to add. Now, there are two portions to this. One is required and the other one is semi-optional. Now, binding is the act of turning our syntax tree, which, as you could have seen, it's essentially a parse tree, keeping all the tokens and all the trivia around it, which means spaces, new lines, and comments. We keep all of that, and binding turns this into an abstract syntax tree that has symbols instead of tokens or identifiers, and type information, essentially. So while Roslyn mostly does this in a single step, because we have bidirectional type inference in the compiler, we do that in two steps. First off, we translate the syntax tree into an untyped tree, which is a simplification on the syntax tree, while we register constraints into our constraint solver. Then we ask the solver to solve all the constraints, which will result in overload resolution and trends. And when everything's resolved, we do a pass on the untyped tree and turn that into the final bound tree, completing the binding process. After that, this is obviously required because we do code generation on the bound tree. Now, after that, we do flow analysis, which is concerned with data flow. For example, if a method returns on all paths and such, or all variables are assigned before being referenced, are all checked in flow analysis steps. Now, it is not very much required for having a working for loop for us, but we will check it out. It will be very similar to how the while loop is essentially flow checked, since we will desugar it into a while loop anyway. Now, how will this binding work? What will we need to check? We will do it in a very similar way to how Roslyn does it, which is essentially a form of duck typing. What we will check if that this sequence that we specify, let me show it on the markdown render. So whatever we specify here as the enumerated thing, we'll have to have a method called getEnumerator that can be called without parameters, just like here. And whatever that returns has to have a move next that can be called like this as a member function, and it has to have a property called current. Now, I'm not sure if Roslyn accepts fields and properties as well. I don't think we will check for that. We will just check if it's a data member, either property or field. We don't mind either. Now, this means that we don't actually check if the thing here has a type of IEnumerable, or that whatever getEnumerator returns must be an IEnumerator. We just check if these members are present, just like Roslyn. Now, this is nice because we don't need to use these interfaces directly, as long as we can conform to these shapes, essentially. So we will support these, even if we come up with our own way to iterate later. This will be a nice way to keep to be compatible with any iterator that Roslyn accepts as well. Well, I suppose since this is probably specified in the C# specs that it has to work this way. Essentially, anything that's written in the BCL, I guess, and is usable in a C# foreach loop. So let's get started with this. Again, we will start by defining nodes for the bound tree and for the untyped tree, and we will have to do that in the in the compiler as well. Now I use VS Code to edit the XML. This is because I really don't like the XML editor of Visual Studio. So we have an untyped nodes.xml, which is the untyped tree, and we have a this is the settings page. We have one called the bound nodes.xml, which is the typed or bound tree. Now you might ask, why is this repetition? They look very similar. Yes, they more or less look dissimilar, but there are some important distinctions. For example, for certain members, we can only contain a promise to some symbol that will be resolved later, and in the bound node we obviously have that referenced already. So if you look at the call expression here, the equivalent is having the function symbol itself. There are also places where the shape completely differs. We have some places where the typing of a subtree needs to be delayed. So there are untyped differ nodes, differ as in executing later or pushing it to later. We don't have that in the bound tree, obviously. So there are minor shape differences and there are member differences. Essentially, we differ very much in what we have available to us at that point. So that justified our differentiation of the two trees. So again, let's copy while. That's the most similar thing we have. And this will be an untyped for expression. And we won't have a condition, but we will have a local. This loop introduces a local for the iterator. And I think we have something called an untyped local, which means that the type of it might not be inferred yet. Let me just verify that. Yes, local expressions, for example, reference this local symbol. So it has to be an untyped local symbol as well. Because during type inference we can have type variables. The locals at this stage are referred to as untyped local symbols, and once we get to the bound tree we will finally have the typed or just local symbols when that's resolved. Now next will be the iterated sequence, which will be an untyped expression. We don't store the type annotation here. That is erased and moved into the constraint dimension of the binding process. So types are not represented here directly. They're pushed into data fields in the symbols and into the type checker constraints and such. The then portion we obviously need. So as you could see in the while expression, we store the continue and the break labels, which are used when lowering. We will have the same for the for expression. They define the continue and the break labels that we can reference later in our go-tos. We don't have break and continue statements. Break and continue are just labels that you can implicitly reference in loops that you can essentially go to. And we will also reference the members that are required for a sequence to be iterable or enumerable, I guess, which is what we have specified here, that we need get enumerator, the move next, and the current. So let's try to come up with the fields that we will need for this. I'll just call get enumerator. I just call the function that, which is going to be a constraint promise. And it will store a function symbol. Now we need two more things. Whatever this returns must have a move next and a current. So move next also has to be a function symbol, and we also need a current, which is not a function but rather, let's just have it as symbol for now, and we will specify it more if needed. So binding, first step, we'll already have to fill out all these members, and because of these promises, we will also have to include a bunch of constraints and create promises from those constraints. Now, as for the bound node, this will be very similar. This is a case where there is no significant shape changes. We can just copy paste our untyped for expression here and rename everything. Now, instead of an untyped local, the iterator will be a local symbol. The sequence itself, it will be just a bound expression. Same for the body. The labels will stay as is. They are not affected by the binding process, and promises are resolved before the last stage of binding is ran. So here we will know everything about the symbols. Okay, that should be it for the bound nodes and the untyped nodes. So let's go into the binder and actually start hammering it. Now, if we run our sample code again that we have here, we will have the binder trip on an unknown node, and we also have some error in the tree. Let's check what that is. Oh, somewhere I left an untied expression in the boundary, I think. Oh yeah. The base type was incorrect. So let's check again. We should trip on the binder here, creating the untyped node. So let's add that case here. We will add it just under the while loop, because we did that so far. It worked out fine. And we'll move it just below the while expression binder. I usually rename this first parameter syntax because, well, that's what it is. It's the syntax for the for loop. And we will have to do our magic here. Now, what will we have to do? First off, the for loop is somewhat special. This is because it introduces a new binder. What the hell is a binder? Well, the binder is the object or class or type what we're in currently. But the binder essentially represents the scope that we're working inside currently. So if anyone's coming outside of the Roslyn world, think of the binder and the binder chain as the scope tree or the scope structure hierarchy, what you're building up during something like symbol resolution. But instead of only doing symbol resolution, we do other things as well, mainly type check outside of trying to resolve symbols. Now, you can see that any binder or any node that introduces a new scope will retrieve the binder for it using this method. This method is responsible for looking up the nearest binder for the syntax, and will connect up with everything else correctly. So we will have to do the same, but obviously currently this method will not consider for expression as something that introduces its own scope. It will just return the binder for the parent, which in our case will be the loop body, the function body, and we can verify that as well. So for it to shut up, I'll just throw, and let's see what we get here. So this is an incremental binder, and whatever is inside is a local binder, and it's declaring syntax is the entire function body, which is not correct. We want the for loop itself to create its own scope. So this means that we will have to change the binder retrieval logic a bit. The meat of that is in the binder cache, which reuses binders for the same syntax nodes. This makes sure that we don't duplicate scopes. And here you can see that for a while expression, we build a loop binder, and we will do the same for loops. And that should be almost it. You can see that this is a private thing, and we call this after walking up the syntax node to the nearest scope defining ancestor, which obviously means that we will just skip past for loops, and we will have to add for loops here as well. Okay, now if we recheck on our breakpoint, we should have a loop binder now, which we do, which is wonderful, which means that this for loop introduced its own new scope, and its parent scope will be the local binder that is responsible for binding the entire function body. So the scope hierarchy is working fine. The next thing that we will have to do, well, we can go a couple of ways. First off, we can copy paste this. We need to resolve the loop labels for the loop binder. If we look into it, we'll introduce the break and continue labels by itself, and it also implements the resolution logic for it. So whenever we look up something, if we are interested in the name, the break or continue name, it will consider these for the lookup. And because this is a local scope, we will only do that if we are interested in locals. We don't disallow them for some lookup. So this should just work implicitly. Let's see. Okay, so the loop label gave us a break and continue label. Wonderful. So it might be weird for you that the binder itself defines these labels. I think this is a pretty nice system for it. It means we never forget to define anything, because we expect all loops to define these two labels. So a loop binder will just define this for us, and we can inject them in the untyped tree when we construct it. Now let's see what else we need. Might be the simplest way to check it is to start writing the constructor. So the syntax is easy. We just remember what syntax node this was produced from. Now we need an iterator. Let's do something like, let's write to-dos, what we don't know yet. So sequence is a to-do, then is a to-do. Continue label is also to, wait, we do have that, so we just leave that as is. Break label, we have that as well. Get enumerator is still a to-do. Okay, so we just have to fill out the rest. And it sounds like they draw the rest of the owl meme. So let's get on with it. The iterator itself is a bit more complex because we have to introduce a new variable. So let's start with something simpler. So the sequence and the then portions can be just bound with the binding call. So sequence will be well, just like here, the then we just call the binding on this child binder, and the sequence itself is an expression, and we need to pass on two things. One is the constraint solver itself, and the other is the diagnostic bag where we shove errors into, and we can also bind the body of this loop, which we call the then. We can fill those out. Now the rest all involve some kind of type checking. So let's start on that. We need to introduce a new local, which is a bit painful. This is because the binder will have to know about it. Now you have seen the loop binder before. It only introduces two symbols, which are break and continue. Now, if you look at something like the local binder, probably our most complex binder, that will go through the declaring syntax and return you all of the locals that are introduced in that local scope. Or if you look into the function binder, then you will see that it also returns all the parameters and the generic parameters that it introduces for that scope. So our loop binder essentially has to do the same. In case of a while loop, it will still only introduce a break and the continue label, and for a for loop, it will have to introduce an additional local for us. So this might not be the nicest thing ever. We might want to, in the future, derive from this binder and extend it with its own logic. But for now, we might just make it an optional property. You know what? Let's do it properly, and we will do some minor refactoring to be able to derive from the loop binder and add the additional iterator in the derived type only. So first off, we will need the same logic. So let's add it as a protected thing. I think it should be an internal protected. I don't know if that's a proper modifier. It will be something like that. We might be able to just make it protected though. This condition, by the way, just checks if we need to add the given symbol to the result set, to the lookup set that we are currently building. So first we check if the name of what we looked up is called break. If it is, then and if we allow this symbol, we have an extra filter because sometimes we filter symbols during lookup. Then we add it to the result set, and the same thing for continue. So I don't know if there's a nice way to factor this out because there are a bunch of parameters. It would be really nice to write this as a local closure, but unfortunately we are unable to do that. So we might just not factor that out yet, unless we find something nicer. So obviously, if we derive from it, we won't be able to make it sealed, and we will add a new binder called a for loop binder. We can seal it just fine, and we derive from loop binder. What are we missing? constructor. Okay, so it definitely needs a parent. Yes, which is the enclosing scope. If you want to imagine what this represents, this parent. And we also need the declaring syntax. Now, what we know about the declaring syntax is that this must be a for loop syntax. So we can just override that property. Hopefully we can. And this will be a for expression syntax. Okay. With that, we have a new for loop binder. Obviously, why we did that is because we want to introduce a new local. And we have to return it in the declared symbols field. So what we will do is add a new property that will represent this new symbol. And I guess we will construct it lazily in the constructor maybe. Well, that won't be lazy anymore. It's not a local expression, it's a local symbol, sorry. We call it the iterator. And I think the simplest thing to do here is to just construct it in the constructor. Which needs a containing symbol, which is easy. Binders keep track of their containing symbols. And we need a declaring syntax. Now here is where it gets a bit trickier. You can see that locals always expect a variable declaration syntax as their declaring syntax. We obviously don't have that, we just have an identifier. So we will have to hammer that a little bit. We need the iterator here. And we will quickly go and adapt the untyped local before moving on with this. So we will just have a syntax node as the declaring syntax. Many things don't depend on this, fortunately. So this is a pretty easy adaptation. For example, we can just make the name a property. And we can also make is mutable just a backed property as well. And we can generate a constructor where we take most of these. Yes, that should be actually fine. And then we will just call this constructor from the other. So containing symbol, we just pass it on. The name we can read out from the syntax. Mutability, I should not have deleted that logic. We will just copy it out. It's not that it's complex, it's just that I don't want to make typos. And finally the syntax itself. Okay, I don't think anything else should be dependent on this being a variable declaration syntax, so we should be good. Okay, but now we have to fill in the remaining things. Now this will be never a mutable variable. And the declaring syntax is well, yeah. It's this. Whoops. Now we have a nullability mismatch here, unfortunately. We just do the nasty thing and suppress it because we're quite sure that the loop binder is always enclosed in some other symbol. We might be able to make this a bit nicer and have proper nullability here. For now, this will be fine. So one last thing we need to do is actually override the lookup logic to consider this new variable here. It takes quite a few things actually. So what I'm going to do is take the loop binder logic that we have here. It's gonna be a bit nasty. I'm just gonna paste it here. So if we have the disallow locals, we obviously return immediately. Otherwise, we'll check if we have the iterator referenced, and for the rest, I'm just going to call the base function. I think that should be it. Almost. We are going to change the type of the binder in the binder cache. So what I'm going to do is that inside build loop binder, we're going to check what kind of syntax we're talking about. And for any other loop, we will just default to our old loop binder, but for a for loop, we're going to build a for loop binder. What are we missing? Oh, obviously the parent parameter. And I'm missing a change here. Okay, let's check if the for loop binder is built for us. We can just go back into the binding process. And oh, we have a bunch of to-dos here. Maybe the easiest way to suppress these are to make these nulls temporarily and then check what kind of binders we have. We also have a problem here. Oh, of course, this thinks that this is still a variable declaration syntax. Now this can just be a syntax node. I don't think anything actually depends on this. So good. Okay, and within the binder, let's see what our underlying binder is. We're in an incremental context, so the outermost binder will always be read by an incremental binder. So to get to the actual binder, we have to look at the underlying thing. And we have the labels and the iterator, so wonderful. Now it's pretty easy to resolve the iterator then. You can just do something like this, but we assume that there's only a single local. And since this introduces its own scope, that will be probably a correct assumption. And this is the iterator. Let's call it that. And with that, we can fill out our one more hole here in the binder. And let's check where we're at. This is my usual working process. I just fill in holes until until we get to a running stage. And then we can discover that not everything works yet. Sequence contains no elements. Oh, of course. Because what we forgot is we forgot to modify the for loop binder. Because it has a property called declared symbols. And this has to go over every symbol that this binder introduces. The simplest will be to append to the basis symbols our iterator. Okay. Did I forget to... Did we forget to put in our breakpoints, maybe? I can also see that we're already getting spam in the Twitch chat. I'm not happy about that. Let me just quickly delay that. Sorry, guys. I wish I knew how to delete a message on Twitch. So please, guys, just ignore that comment if you're watching this live. I will figure out how to delete messages soon. I swear. So, for some reason we are failing a bit earlier. Let's see why. What's actually calling this? Oh, the body, of course. The body of this method references this iterator, but we haven't registered our iterator variable in the type system. So the constraint solver has to know about this variable. So let's just add it. I don't exactly remember how we do that. Maybe we just cheat a little and look into bind variable declaration. Okay, that also looks up the local, and okay, it's just declare local. And we will also steal whatever is above that, because we'll have to consider the optional type annotation that the user makes. So let's go navigate back. And so the iterator can optionally be typed, or rather the element type can be specified. So if we have an element type specifier, we will check out what kind of type that references to, and the binder again resolves these to type symbols directly, and then we can just declare this local. Okay, we have a bunch of errors, and this is because VS decided to pull in the API semantics namespace. Sometimes it does that. This might be the curse and the drawback of us keeping a parallel hierarchy here, one for API and one for the internals. Sometimes it just automatically pulls in from API instead of asking us. Yeah, this is a pain, but once you get used to it, you will delete it out of reflex when you see a bunch of errors suddenly pop up. So this is not the declared type, this is probably the elements type. Let's call it that. We might not even need it because it will be inferred from somewhere else. So, or specified. Let's see if the binding runs up until this. Yes. And we have the iterator, and it obviously doesn't have a type yet. There was nothing to infer it from, but everything else ran. We resolved all the labels, the iterator from the binder. So let's move to the next step. We still have 3 things to fill out. One is getting the enumerator, one is getting the move next, and one is getting the current property from the sequence. let's do them here. So first off, get enumerator will be a method that has to be defined on the sequences type. So we can use a constraint, an overload constraint on that, which essentially emulates a call and checks what it resolves to, and it will return us a promise. So it will take the set of functions that we allow for overloading. Now, I was hoping that there is a simpler way to do that, because that means that we will first have to retrieve all the functions from this type. I guess we can do that. So then first we use a member constraint, and the accessed type will be whatever the type of the sequence is. So we can just do sequence.type required. Not all expressions are properly typed, so type required just says you must give me a type, otherwise it will be an error. And the member name will be get enumerator. And we get a type variable for the member type, which we will ignore because we are in the hopes that this will be a bunch of functions. Now, the painful thing is that now we will have to wait for this promise to get substituted to be able to construct our overload constraint, but it's not that big of a deal. Our solver is capable of this. So we can just say that constraints.substituted. This is also a promise, and we need to specify what we are trying to wait for. Or is it a wait? Oh, we call this a wait. It should be called substituted as well, because soon we are merging type variables and promises anyway. It will be a larger rework on the solver. Because they represent the same, essentially the same concept, but we started them separated, and now it's hard to get rid of them, but we will soon. So whenever that is, I don't know why I wrapped this in an if statement. We don't need that. We don't know what we're returning from here yet. So whenever the get enumerator methods got substituted for something, we get the members, we can get this lambda called. So here we can say something like we can access the result of this promise, and we can say that functions equals, switch on this, and we have two cases to handle here. We don't really care about error handling as for now. We will leave that for later. That's kind of boring to watch. So for anything else, we just throw. And we have two things to handle. One is an overload symbol. We model overloads as a symbol, even though they're not actually symbols. We might want to rename them as function groups later. Or if you have a function symbol, we just wrap that up as a singleton in an immutable array for now. And then we have an immutable array of functions that we can pass into the overload. So we have functions, and since getEnumerator is called with 0 arguments, this will be just called with an empty immutable array, and the return type we actually care about, because this is the enumerator type. Now this is yelling at us because we need to actually return something here, and we might just return the enumerator type itself. Okay. Are we done with everything? So we need a constraint for the get enumerator. So we need to return both the promise and the enumerator type. Okay, so we do something like for now we just return them in a tuple, I guess. This is not the nicest thing, and you will see why in a bit. Once we have to modify the solver logic itself. Why is it yelling at me? Do I have to explicitly specify this return type here? Maybe. This will be ugly. You happy now? No, apparently it's not. Oh, it's because this is a promise, of course. We can deconstruct that. This is a promise of pairs, so... Huh. Yeah, let's not store them here yet then. And we won't even return them. We will probably have a delay node that will be ran once the get enumerator promise is resolved. Let's be consistent and call this promise as well. First off, let's see if this method runs at all. Okay, we don't specify the return type here. We might actually do that. Because the way that the solver currently works is that it will pick out individual rules. So let me show what I mean by that. We have this gigantic function that we're soon eliminating with something smarter, and it's just trying to look up constraints that it can solve. And because await constraints are generic, I can just query for in a nice way for them. So I just did the ooga booga thing and copy pasted dequeuing the await constraint with the four different things that we use it for currently, and it happened to be these four type parameters that we use it with. So I'm just going to look up something like type symbol is surely dequeued, so it's considered while solving. And I'm just going to substitute this. This makes sure that this await constraint is picked up by the solver eventually. So let's see if this await is ever called. Yes, it is. It's called. Hot reload. I don't think I meant that. Did I edit something by accident? Okay. So we found this single function get enumerator on the type, on the sequence type. We need to go a bit down the call stack to be able to see it. Oh, we're not even in the same call stack anymore. So just to show you guys that the sequence.type required. Oh, it's still a type variable at that point. This is quite sad, but once it gets substituted, I think that the promise actually contains the constraint itself, which contains the accessed type. Yes, you can see it here. It's an enumerable, and it has a bunch of members that we crashed on here. That's not important. The important part here is that we could resolve this singleton function from this, and we could build an overload promise. Now, you might ask, why the hell build an overload constraint here when we already have a function? Reason is there could be a chance that this is overloaded, and we're going for correctness now. So the simplest thing is just to build another promise that will be resolved once we know which method to call, which will probably be immediately, unless there are like conflicts because the user defined to get enumerables functions with 0 parameters or something, or have a variadic one, but that will probably match less based on our current overload resolution rules. Our overload resolution is already quite complex because we already have generics, variadics, and subtyping, so it's already a mess. Okay, we have a promise for this overload, which means that we have the get enumerator resolved. Let's just call this the get enumerator promise, and let's call this get enumerator functions. Yeah, I'm a bit inconsistent with using methods and functions. It's fine for now. We're also missing configuring these constraints for with diagnostic information. Each constraint returns a promise, and the promise has a way to specify some diagnostic info, so if it fails to resolve, it knows where to point in the source code and such. This isn't a nice system, and we're currently in the middle of reworking it, but I'll just leave to-dos here because for now we will probably just specify them, but I'll do that off stream because it's quite a boring thing. So whenever we are registering a promise, I'll just write a to-do to configure it eventually. So we have the enumerator type. We have 2 members on it that we need to configure or locate. One is the move next, and the other should be the current member. Now, since we have an enumerator type here, we can do that. We look up move next. It will be a very similar pattern to what we did here. This is going to get quite nasty and nested. We will need a couple of utility functions to make this nicer. We could probably write something that automatically awaits, filters for functions, and registers the overload. But we will not do that today. Today we are just going to complete this in the simplest way, and we will clean up later, maybe in a different stream, but that might be very boring. So we need another member constraint that we need to add on the solver. And the enumerator type will have to have a member called move next. And we don't care about the type of it because it's probably an overload set or just a single function. We really don't care about it. But once that gets substituted, so we'll have another await inside. This is the beauty of bidirectional type inference. We'll have to wait quite a bit for everything to get resolved. So once we have this resolved, we can write another lambda that gets called when this is substituted. we will have a very similar switch here. This is something that we probably want to eliminate as well eventually. So this is the move next functions. And we want to do an overload on it as well. There's a very slight chance that there are multiple move next functions if the user writes some funky code. So we will just use an overload constraint again. And this is the move next promise. And this has to be a bool actually. So we can add a constraint to make sure that the return thing here is a bool. I'm not sure if Roslyn accepts anything that's convertible to bool or can be used in a condition, but we will just assert for now that this has to be a null, a bool. Sorry. So this is not the correct set that we pick from. Again, we need null parameters here. And we will add a constraint to make sure that they are the same type. The bool and move next return type has to be the same, so we can use it in a while loop as a condition. And for now we return null from here as well. So this is quite complex, but let's check what we have built so far. Let's try to go here and see if we have resolved something. Apparently we probably did. At least we resolved the move next functions, and we found a single one, which is of type bool, so that's wonderful. So now we will have to find a way to propagate this all out, and we will also have to locate the current member. That might be a bit simpler, so let's do that next. That will be another member constraint, of course. So this is the current promise, and again on the enumerator we search for something that's called the current, and we actually care about this type because this type has to be assignable to our iterator variable. So if you have picked up the theme for now, this will be another constraint. Of course, don't forget my to-dos here. We will have a lot of to-dos to clean up after the stream. So the target type that we assign to is going to be the iterator's type. It's an untyped local. Oh, we have the element type to refer to its type, of course. Okay. And the assigned type is going to be the current type. And okay, that we don't store the result of this assignable constraint. If this fails, we will just get an error, but we don't really care about it. Sometimes it aids in overload resolution and such when we know that something is assignable to something else. So now the question is, how do we propagate all this out from an await constraint? And my gut feeling is going to be that this is going to be a delayed node again, which means that until we get these things substituted, the rest of the binder will wait on this node. It's not as complex as it sounds, as you will see. So we have the current promise here, which we obviously need to pop into here. We have the move next promise here, and we can do we can actually return that here, which means that this will be we don't return a type symbol anymore, which means that this is a promise of promise, but we have a utility function for that to unwrap a nested promise, because this is quite a common operation actually. So this is going to be the promise for move next, and we'll likely do something similar here. No. Okay. And we have the get enumerate promise here as well. So here we are actually ready to return the expression from this lambda. So that's what we're going to do. It doesn't need to be nullable anymore, and we're just going to copy this in. Oops. Oh, for some reason I didn't indent. And we can finally fill out the rest here. And of course this will be a promise of an untyped expression. And we can just wrap this into a delayed expression. And the type of that, that's actually very simple. The type of this expression will be unit, as for loops are just like while loops, they return the unit type. Okay, if you wonder what this delay expression does, it waits for this promise to be substituted, and then it takes the lambda, it runs the lambda. Once the substitution is done for this promise, it computes the expression, and then it will return that instead of itself. So this is a way to wait on something before continuing the binding process for a type. Now let's see if this actually works. It looks like it does, and we have a bunch of things here. Now obviously this isn't the interesting part yet. We need to see what things we get once we move on to actually converting this untyped tree into the bound tree. So let this run on, and let's hope that we are dying at the typing stage. Yes, we are, which is nice. And the unknown node here is an untyped for expression, which means that the delayed expression got unwrapped, and we're trying to bind the for itself. Again, let's copy the while expression. And we will move this right under while expression now. Fortunately, typing is very simple. It usually just means that we are unwrapping the promises, the type variables, and we are constructing the final node. I almost feel like that this could be almost entirely source generated later on. I'm not quite sure yet. There probably will be some edges, but for the most part, as you can see, we just recursively call the typing method for every element, unwrap the promises that we had, and then construct the final node. So let's do that. First off, we need the syntax, of course. We can just borrow that from the untyped node. Then we need the iterator, which we can ask for a typed instance once the solver has run. Now the typing phase is always run after the solver is finished. So we can ask for the typed local based on the untyped local. Then we need to type the sequence as well. Then we need the body of the loop. And then we need labels. Fortunately, those are already resolved. First we want to continue. Then we need the break label. I'm going to break this up into a multi-line constructor because we have quite a few parameters. Then we need the get enumerator, which is a promise that we resolved. I don't know what our policy or convention here is. I'm just going to unwrap it in line. So I'm going to do this, and I'll unwrap the move next as well. And we unwrap current as well. Let's see what we're getting here. We get to bind to the end of binding, which is really nice. Okay. I don't think that we have explicitly typed it, so I'm very happy to see that the solver inferred that this is an int32. Wonderful. The sequence itself is a bound call expression. And it has everything in there. You can see that the bound node is pretty printed, so you can read it a bit better than the untyped tree. Now the then is a block expression, and it has a call to write line with our value. Okay. And it's calling the int32 overload of that. We have our labels, we have our get enumerator method, well typed, loaded from metadata. Move next as well, wonderful. And current is inferred to be an int32, and let's see what it believes it is. Somewhere we can actually peek into the type. Maybe I have to navigate from here because then we can see its type. So let's check current. Current is, well, it's a promise here, but the result is a property. So that's wonderful. It's a property instance because it comes from a generic context. So I think that we are done with binding, which was probably the hardest part of this. Let's see if we crash anywhere. Probably not, and this is because there are no hard checks for code generation and flow analysis. So let's commit because we have come quite far. Yeah, we hammered a lot on the binding, and we also created a new kind of binder just for loops. So before I forget, I really like to leave a small documentation comment above binders as well. So for example, This just says that it binds break and continue. So let's add a doc comment for loops, which binds the iterator. This should be fine. Now we can commit. And the next logical step would be to move to flow analysis. Now, what I suggest is that we skip flow analysis for now. We can still do it in the stream, but I think that we can do lowering first, as that's a bit more interesting, as we will get code finally running. And lowering itself is also a more fun process. It's actually a part of the compiler that I personally really enjoy working on, as it's really nice to just de-sugar things into their more primitive ways. You will also see how the binder is relatively nicely structured, or the lowering process, sorry. But before that, let's take 5 again, and we will continue at, well, let's take almost 10 then, to make it a bit easier to track when we're coming back. Let's continue this at 16:30. So be right back, and stick around for lowering, after which we can finally run this for loop, hopefully. Alright, let's continue. Hope you guys aren't too tired yet. So, wow, it's been 2 hours. No wonder I'm getting tired. So, where we left off, we are done with syntax, we did Lexing, parsing, and we did binding. So, we have our for loops in a neat abstract syntax tree, or some call it a semantic tree, I guess. We call it the bound tree, where we have all symbolic and type information that we would ever need. And the next logical step in the compiler pipeline would be flow analysis, but we will temporarily skip that to get something up and running, and we will do lowering. So we will rewrite this form into this form, essentially to avoid having to write code generation directly for each loop. We will still do flow analysis later, but it's an optional step that we can essentially just skip and get away with it for now. So let's close everything here. We opened quite a few tabs, and let's go into lowering. So for this we will open up the local rewriter, which is essentially the thing that is desugaring or lowering the higher level language elements that are local in function. For example, you can see how variadic calls are desugared into constructing an array, assigning the elements, and then calling the method with that list of variadics here. Let's see if we have a simpler example. If expressions are lowered into conditional go-tos and labels, and of course a result local if the expression evaluates to some value, or relational expression chains. Draco allows you to write something like x less than y less than z, and we rewrite that into pairwise comparisons and lazy AND expressions. And expressions are rewritten into if expressions, and so on and so forth. So this is how we avoid needing to write code gen for many high-level constructs. That would be a pain. Now we also do this for while expressions. While expressions are being rewritten into a pair of labels and a conditional goto. Now, fortunately, we don't have to rewrite to the labels directly. What we will do is we will rewrite our for expression into a while expression, and then we will just let the compiler lower from that. Now, the rewriter is also generated from the structure, so we will have a visit for expression already. We don't need to write any of this, it's generated from the XML. And as you can see, almost everything is called to be desugared immediately. So the condition is being desugared, the body is being desugared, and then it's being used in the construct. Now, since we know that we will just call desugaring on the result immediately, we won't desugar the individual elements. Now, this is quite an unusual behavior, so we'll leave a comment for future self or other contributors here. Okay, and we start each lowering step with a block command that describes the operation. So let's keep ourselves to that. And I think we just do something like this to denote it. And then we write an arrow like this, and here we just write that same loop that we did manually almost 2 hours ago. So we need to return a single node. This means that we will wrap this up in a block here. Now that's not unusual to wrap up these desugared elements into subblocks. As you can see, almost everything has it, because this is because we always return a single bound node from desugaring step, but the desugaring of this obviously will be more than one statement. So the simplest thing to do here is to just unwrap it. So first off, we call get enumerator on this sequence, whatever that is, and then we just do the usual C# way of iterating, or rather, I think it's universal to .NET. I am not sure what F# uses. Okay, one note, this isn't the complete loop yet. Again, we should be wrapping this in a try finally if we were truly conformant to what C# does. And if the enumerator is a disposable, we should be calling dispose. So we will also leave it to do here. Okay, so rewriting this should be pretty simple. We have a generated API, again generated from the XML, a way to easily construct bound expressions. We just call them bound block expression. This is because bound is redundant. This is all in a static class that we just imported here. And the block expression, well, we don't need the syntax. We have multiple overloads, and we will use the ones that don't need syntax trees to be passed in. This is because lowering only happens when we are past this stage where we expect errors. So here we drop everything that we don't need. Now this introduces a single local called get enumerator, and we need to allocate a new symbol for that. I think we can just do something like instantiating a new synthesized symbol. So let's do that here. Yes, we have a synthesized local symbol, and it takes the type. And the type of that will be whatever the get enumerator returns. So this, and is mutable is going to be false. We don't mutate it, we don't rebind it. Essentially it will be mutated because we call move next on it, but is mutable here refers to rebindability. We cannot reassign it. So locals will be just a single element, and the statements will be, well, all of this. It's going to be 2 statements. And I think we need a value as well. Now we have a singleton for that, because many blocks don't really return anything. So it would be a waste to allocate something for them each time. Now the first will be an assignment. We don't need to declare it. The block already declared this local. The structure of the bound tree is very different from the syntax tree, because this is modeling semantics directly. So what we need is an assignment expression, and we do not have a compound operator. Compound would be something like plus equals or minus equals. Then you would refer to the binary operator here that is being referenced in the compound. The left side will be a new L value. This is a local L value because we're referencing the local. And the right side will be calling the get enumerator on sequence. So it would be call expression. The receiver is the sequence. The method that is being called is get enumerator, and arguments is just an empty list of expressions. Okay, I think that should be it. Oh, and obviously we expect a list of statements here, so we wrap them up in expression statement. And the next thing that we do here, oh yeah, we probably need to specify that this is going to be a bound statement array. Yeah, we do that as well here, because this is obviously returning a more concrete type and C# gets confused. So the next will be the while loop itself, which is an expression statement on its own as well. And this one needs a condition. We need a then, and we need the 2 labels. Now the 2 labels are very simple. We just forward them, essentially. They will be the same labels. The condition will be this, so we need to call move next on the enumerator. The receiver will be a local expression referencing the enumerator. The method, again, it's already stored in the node. It's move next, and there will be no arguments. can just copy this. The body of the loop, very, very simple. We just pass that on. And I think we are in the clear here, except that this really wants to be a different kind of immutable array. Okay, oh, one more thing, of course, within the body, we can just, we need to include the, actually the sugared body, so this won't be this simple. We will have to create a block here again. This fortunately will we introduce the iterator here? Yes, we do. We need to introduce the iterator here. So the local will be the node.iterator. Oh, and we need to, of course, wrap that in an array. We'll have a list of statements. And we will need to have a value, which will be unit again. And here we need two statements in total. First off, we need to assign the enumerator.current field into the iterator variable, and then we will have to include here whatever the body was. So let's do that. It's going to be another assignment expression. The compound operator will be a null again. The left side will be a local L value, and the right hand side will be a property get expression. Now here's where we will do a little hack. So the receiver is not part of the hack yet. It's going to be the enumerator. So local expression of enumerator, but the getter is expected to be a function symbol. Now we didn't assert that this has to be a property yet, so we will do a hack and just cast it here. I am not sure if we want to assume it during type checking or if we want to assume the type of current at all anywhere, so we will just delay this decision, and until now we will just do a hard cast here. This way we can actually reference the getter here. Oh yeah, of course we need to wrap this in an expression statement, and we also want to make sure that this is a bound statement array. Now we will see that the getter is nullable, and it's yelling at us that this is nullable, and it is. Obviously the current can be a set only property, so we need to check that. We will just leave a to do here again and assume that it exists for brevity, as we have been going at this for 2.5 hours already. Okay, so in this block, first we did an assignment, And then we need to actually include the then portion. So essentially the user's block here as well. So we can just do this. And again, we need to wrap that up in an expression statement. And that should be it. It looks quite complex. It's really just doing this with a gigantic constructor. Let's see if this works. I am quite scared to run it. Okay. We have an unknown operand, a null. So something, a store instruction. This is in the CIL. So this is in MSIL code gen already. So quite far in. And it tried to encode a basic block. And I suppose the basic block contained an instruction, a store that had null as its source, which is quite unfortunate. Let's see why that is. Okay, so this was probably in the main procedures. We don't have any more procedures. Let's see if we are missing something in local rewriting. Let's see if everything has a non-null value. So enumerator is not null. Sequence is not null. This is not null. So as far as I can tell, let's look at the result in a more brief way. So it introduces the enumerator, that's fine. Okay. It also has two statements, one of which is an assignment to the local, and it assigns a call. Okay, this looks fine. And the next one is a while expression. Oh, I know what we did. Of course, we need to de-sugar this. So the rewriter assumes that we returned everything in the most desugared form. So let's just name this for simplicity, and we will do something like result.accept this, which will desugar the while loop as well. Let's see if we're failing anywhere now. No, we're not. That's really nice. Nothing's happening because we are only compiling. So let's flip the switch here. And instead of compiling, let's run. Awesome. So we are getting for loops working. Of course, the extension will still yell at us from very weird messages because we didn't recompile the language server. We might do that in a separate stream where we do the grunt work for loops. We will add it to the syntax highlighter, add inlay hints for this variable in case it's not specified by the user, and so on. But for now, we will just deal with this. Let's do some sanity checks and let's see if we can do something like breaking in case I is 5. Yes, we can. Good. Let's skip even elements. Awesome. So it looks like the bare fundamentals are working, of course, without any proper error checking. So let's commit, because we did a lot. This was quite a bit to lower. And let's do our final boss, which is flow analysis. Now I don't want to skip this because this is part of the compiler, so it's not like a side thing that we have to do like error checking or tests. This is something that fundamental correctness relies on. So let's try to come up with a test case here. Let's assume that main has to return an int, and we return I. Let's see what happens, what the compiler does. Let's just compile. I don't want to do crashes here. Okay, so there's no first instruction. That's we're crashing the compiler, which is kind of worrying here. Let's check why exactly. Let's see if we have any errors in the compiler, because then we shouldn't even continue into code gen. But it looks like we do not have errors, which is of course a problem, because this could very well be the lack of flow analysis here. So what what flow analysis should pick up on is that this for loop might run 0 times. Now, obviously, we do know that it runs at least, well, it runs exactly 10 times, but our flow analysis should be a dummy and assume that this for loop might not run at all, just like while loops. So let's jump into flow analysis. Now that's yet another part of the compiler. And it's named flow analysis, so it's pretty easy to locate. And all passes derive from the same common type, which is called flow analysis pass. So if we implement checking for loops here, then all other passes will consider it, because essentially all this does is that it's calling meet, join, and clone onto this state, what we're considering. Now, if you're into lattice theory, then you will know what these operations mean. I won't pretend that I have a too deep understanding of them. I just implemented them once, and since then I rely on many tests to make sure that it's correct. So let's look into how we handle while here. And again, let's copy it. We'll probably do something very similar. So yes, we will join in with the continue label, but right after we have evaluated the sequence once. We only evaluate the sequence one time. So this is also very similar to abstract interpretation. We'll just copy this. So if you know that term, we're essentially doing that. Then we will be at the continue label, and we don't have a condition, but we do run the then body part and join in on the loop back to the continue label again, and we will be in the break state, which is essentially the break label. Okay. Is there anything else we need to consider here? Let's look for the bound for expression. So the iterator is inert, it's just a symbol. Sequence, we started evaluating that. The then part is the thing that runs optionally, and the rest are symbol references. So I think this should be it for loops. Let's see if we're actually getting an error this time. Yes, we are. We do not return all paths, and to fix that, we need to do something like this. And it works. So I think that concludes. Let's commit. And I think we can finally publish this branch because we did make something that works. So, any questions? I will probably not stop recording in case there are interesting questions popping up. I'll wait a few minutes. If there are questions either on Twitch chat or in the Draco Discord server, I'll be happy to answer them. Okay, no questions this time. We'll probably have another stream where we will go and do some of the grunt work. I won't promise that I'll show the entire process. Again, things like error handling aren't particularly interesting, but it might be fun to see how the tooling integration is done. So we could add inlay hints in the language server. We could add syntax highlighting for the for and in keywords, and so on and so forth. We will plan that later. The recording will be uploaded to YouTube. I hope it will be of decent quality. This is the first proper stream I've done. Well, the first one that actually resulted in a successful outcome for the compiler. So thank you everyone for watching. Have a good one, and see you in the next stream, hopefully. Bye bye.